Okay, today we are going to start analysis of frames. I will start immediately by solving a problem. Example 1. It's required to draw the normal force diagram, shear force diagram, and bending moment diagram for the shown frame. Now we have a frame like this. These distances, we are having 12 foot, and 8 foot. We are having here fixed support and hinged support. This is point A, point B, point C, and D. And we are having here distributed load like that. This distance here is 6 foot and 6 foot, and the load is 5 kPa per foot. And there is a concentrated load of 38.7 applied at point D. Now, in order to solve for the reactions, we are having here vertical reaction at A and horizontal reaction at A, vertical reaction at E, if this is point E. So how can we solve for the reactions? And of course we are having moment reaction at A. Now we are having here an intermediate hinge, so we can take moments about point B from the right hand side. The only unknown will be the vertical reaction at A. If we did this, we are going to get 42 kPa force. Sigma Fy is equal to 0. Then we are going to get the reaction at A. It will be a downward reaction, and its value is 3.3 kPa. Sigma Fx is equal to 0. The resultant of this force is 30. There should be a force here equal to 30. If you want to get the moment reaction, we can take moment about point B from the right hand side. So the reaction times its distance should balance with the moment. The moment should be in the other direction to be in equilibrium, and it is 39.6. Very good. Now we will start to draw the normal force diagram, the shear force diagram, and the bending moment diagram. So this is the normal force diagram. First of all, we have to define where should we draw the positive and the negative values for the normal force. We always imagine that we are standing under the frame. The near side, we are going to draw the negative normal force, and the far side, the positive normal force. So for the beam, the positive normal force will be drawn up, and the negative normal force will be drawn below the datum. And for the column, since we are standing here, so this will be the positive side and this will be the negative side. Very good. Let us start part by part. For the part AB, if we are taking a section here, as usual, and we are taking the left hand side, okay? Now, if you cut a section here, the internal force will be in this direction to balance with the external force. So the internal force is getting out of the section So we are having here tension. This situation will be the same if you are cutting a section here, or a section here, or a section here. Throughout the beam ABC, we are having positive normal force. So I'm going to draw here above the datum positive normal force, and its value will be 30. We have to elaborate on the magnitude of the normal on both sides of the diagram. Very good. If we cut a section here like this, now if you cut a section, don't tell me you are taking this part only, because if you are taking this part only, you will be cutting through another section here. You have to take either the right hand side or the entire part of the frame left hand side without cutting another section. If you are taking the left hand side, you will have the 30, and this will balance with the 30 kips force applied on the column. They will cancel out. Therefore the normal force is equal to 0. If someone else tried to determine the normal force from this section from the right hand side, when you are cutting here, there is no forces applied in the horizontal direction. So this means that in this part, I have 0 normal force. For the column, to determine the normal force in the column, I will cut a section. Okay? If you cut a section like this in the column, we are having the applied reaction 42. How can this be in equilibrium in the vertical direction? Take care, we don't consider the horizontal force, because this force is causing shear and bending moment, but it doesn't cause normal force. If you want this part to be in equilibrium in the vertical direction, there should be an internal force in this direction like this to balance with the vertical reaction. The internal force is getting towards the section, it's causing compression. What difference will it make if I'm cutting a section here, or a section here, or a section here? The condition is the same. Therefore this 42 kips force is causing normal force compression throughout. I need to draw this. On which side? We are always imagining ourselves standing under the frame, so this will be the near side, this will be the far side. I'm going to draw the normal force. Since it is constant, it will be drawn like this, and it is negative. The magnitude is 42 and 42. This is a complete normal force diagram. It gives us an idea the magnitude of the normal force. How does it change throughout the frame? In the part ABC, we are having tension 30. In the part CD, we have no normal force, and in the part CE, we are having compression. Okay? Now let's draw the shear. The same thing. For we are imagining ourselves standing under the frame, the near side will be negative and the far side will be positive. And also here, the far side will be positive, the near side will be negative. Okay. When we are drawing the shear, we are concerned about the forces normal to the central line, not parallel or not in the same direction of the central line. So we are going to start from the left-hand side as usual. If you are cutting a section here, you are having the reaction is downward. So it is downward on our left-hand side, then it causes a negative shear. So the magnitude of the shear here is negative, and it is equal to 3.3. Why did I draw this under the datum? Because it is a negative force. It is a negative shear force. Now, the condition will be the same throughout. You don't have any applied loads here, right? We don't have any applied loads in the part ABC. Therefore, the shear force will be constant as long as we don't have any loads. This will be constant like this. And the magnitude is 3.3. Very good. At point C, we are having a sudden change in the shear because we are having the 42 kips force. So this is upward, it will cause sudden increase in the shear. We have reached 3.3 minus 42, it gives us 38.7. So this will be 38.7 Of course, it will be constant because there is nothing in the part CD applied. So the shear will be constant, and then we are having a force pointing downward. It causes negative shear. It will get us back to zero. Then we finished the shear diagram as usual for the beam. طيب. For the column CE بقى, how are we going to work? Imagine that we are standing here under the frame. Very good. Where is our left hand? This is our left hand. So we are going to cut a section like this. See? I am cutting a section like that. I should take all of the forces on my left. This is my left hand side. I am having a force here pointing downward, and its magnitude is 30. This 30 is causing normal force in the part ABC, but it causes shear on the column CE. And what is the sign of the shear? It is on my left hand side and downward, then it is 30. Now you will find that it is drawn here 30 like this. From this point to this point, I have no loads applied. Therefore, this part will be constant like this. Its magnitude is 30. Maybe one student will ask me, what will happen here? We are having interference of the diagrams. We like this. We like the diagrams to interfere with each other. It shows that the problem is more complicated and more precious. Now from this point, we are having an applied distributed load. It is pointing in this direction. So when you are taking a section here and you are counting all of the forces on your left, this is on your left hand side and downward, and this force is on your left hand side and upward. So it is causing positive shear. Till you reach this point, you will find that the 30 will balance with the 30, so we will reach here 0. How should we connect between this 30 and the 0? By a straight line or a curve by straight line. Why? Because the load is constant. The shear is the integration of the load. Therefore, I'm having here this part is straight like this. This diagram gives us an idea about the variation of the shear throughout the frame. If this frame is going to fail due to shear, where is the first part that will fail due to shear? Is this part, because it is subjected to the greatest amount, which is 38.7. After that, the column is supporting greater amount of shear, and of course the least shear is applied on the beam ABC. Now let's draw the most important diagram, the bending moment. Let me erase this first. We need the shear, so I'm not going to remove the shear. This is 38.7. The bending moment is the integration of the shear. So they are both drawn together. Okay. Type. Let us start in the part ABCD. Now I'm working as usual from the left hand side. Now when you hide all of the frame and you just take the left hand side, you are going to have the moment reaction. The tail of the arrow is under the datum. We are drawing the bending moment on the side of the tail of the arrow. Therefore here we are having this magnitude is 39.6. What is the magnitude of the bending moment here at point B? It is 0. Type. How would we connect the bending moment 39.6 with 0? by a straight line. How did I know this? Because the shear is constant, the moment is the integration of the load. يبقى therefore this is a straight line. And of course, this will be positive. Take care that for the bending moment we are reversing the positive direction and the negative direction. This is the negative and this is the positive. And here on this side, we are having this is the negative side and this is the positive side. Very good. طيب. At point C, take care بقى. At point C, we are having three intersected elements. Okay? So point C, if I'm going to elaborate on point C, it is like this. It is basically three intersected elements. We need to calculate the bending moment left of C and right of C, and the bending moment applied on the other section will have to balance with that. طيب, what is the bending moment here? We can take the left portion, okay? I will multiply 3.3 by 24, and I'm having 39.6 opposite to it. The result here will be, if we did this will be 39.6. How did I calculate this very fast? See, this if you are working with the traditional method, you are going to say the moment MC left, as I said before, this force or this moment is causing positive moment, so it is 39.6, and the reaction is causing negative moment because it is rotating such that the tail of the arrow is above the datum. So it will be negative 3.3 multiplied by 24. This result will be negative 39.6. Since it is negative, the tail of the arrow is above the datum. A smarter student should be able to determine the moment at point C left by another method. Now, we are having here constant value for the shear, right? What does this mean? It means that the slope of the bending moment diagram is the same. Therefore, he or she will just complete this line like this. Since this distance is 12 foot and this is 12 foot, by similarity, this value should be also 39.6 negative. Either that you get it from the relationship between the moment and the shear, or you get it by the first principles. Type, what else? Take care that this point is 3 points. You need to equilibrate the moment on this side and this side on this side. This side is easier because all what we have is the 38.7 Kipps force. So you are going to multiply 38.7 multiplied by the distance, which is 8, and this will give us the value. If you did this, it is 309.6. Now, how can the point C be in equilibrium? This is 309.6 and this is 39.6. Therefore, there should be a moment applied on this side so that the summation of moment is equal to 0, and this will be 270. Okay? So let me draw what we did now. We are having, this is negative, and here we are also having negative moment. The moment here is equal to 0 and the moment here is 309.6. Now I will draw the bending moment on the column. Take care. We are drawing the bending moment on the side of the tail of the arrow. The 270, the tail of the arrow is on the left hand side. I'm going to draw the 270 here. Okay, very good. Now I want to determine the moment at this point here. What will be the moment at this point? Either that I will take the entire frame, the upper part of the frame, or the lower part of the frame. The lower part of the frame is easier, because if you want to take the upper part, you have to take the moment of this force, the moment of this force, the moment of the horizontal reaction, and the moment reaction. But if you take the lower part, you just have the resultant of the distributed load, which is 30 multiplied by 3, which is 90. And how is this? What will be the direction of the moment? It is rotating like this. يبقى the tail of the arrow is on our left hand side. يبقى therefore we are going to draw here on this side we are having 90. How did I get the 90? We are having 6 by 5. This gives the resultant force, which is 30, multiplied by 3 is 90. And why did I draw the bending moment on this side? Because the tail of the arrow is on the left hand side. This is the direction of the bending moment. Okay? طيب, how do I connect the 270 and the 90? We are having here the shear is constant, يبقى therefore the bending moment is linear. يبقى this part we are having the bending moment is linear like this. Is this positive or negative? It is positive, because we said that the near side is positive and the far side is negative for the bending moment. Okay, who can tell me the bending moment at point E? It is equal to 0, because if you cut a section like this, there is nothing except the 42 kips force passing through point E. It will not cause any moment. So this means that the bending moment here is 0. Again, now for this portion, we knew the bending moment at the beginning, and we knew the bending moment at the end, and we are having distributed load. Again, we are back to the method of superposition. So we are going to connect them with a straight line, and then we are going to suspend a parabola. What is the magnitude of this parabola? It is WL square over 8. We are having W is 5 and L is 6. Therefore, if you draw the parabola, it will be like this, and the magnitude is 5, which is W, times 6 square over 8. Okay? So finally, the bending moment will be like this. As a reminder, now we are drawing in our course, in this course, the bending moment on the tension side. Always, whenever we are having the arrow in this direction, where is the tension and where is the compression? Here is the side of the tension and here is the side of the compression. So we are always drawing the bending moment on the tension side. What does this diagram tell us? That the bottom fibers of the frame is subjected to tension, because the bending moment is drawn at the bottom fibers. And here the bending moment is reversed. The bending moment at the upper fibers, and the bending moment is on the left hand side of the column. So if this frame is made of reinforced concrete, we all know that the concrete is weak in tension and strong in compression. That's why in 302 we reversed the direction or the side where we draw the bending moment compared to 212. Okay? Now, according to the bending moment diagram, since the bending moment diagram is drawn below the datum, it means that the concrete will start cracking here, because we are having tension on this side. Why will it not crack here? Because the concrete is strong in compression. It doesn't need any help. Okay? Now I'm having the bending moment now is reversed. So the cracks will appear on this side. Right? Maybe the cracks here is severe because the bending moment is 309 compared to 39.6. طيب, how about the column? The column, the bending moment is drawn on the left, on the near side when you are standing under the frame, which means that the cracks will appear on this side. How can we prevent this frame from failure? We have to help the concrete. Wherever we are having tension, we have to provide steel reinforcement. That's why you see steel reinforcement in the beams or in the reinforced concrete structure. The steel reinforcement will take the tension, so it will close the crack. It will have to be perpendicular to the crack in the same direction of the tension force. Okay? Now, if you are bad in the structures and you drew the bending moment wrong, you reversed the bending moment, what do you expect? You are going to put the reinforcement in the wrong direction, so it will cause failure. That's why you are taking 302 in a separate course. Now here we are having the bending moment is up, the cracks will be up, therefore I will have the main steel reinforcement will be located at the upper part of the frame. And here we are having the bending moment on this side, the steel reinforcement will be located on this side like this. It is our job in this course to tell you where should we put the steel reinforcement according to the bending moment diagram, but the calculation, the amount of steel reinforcement here and the amount of steel reinforcement here will be taken in another course 305. Okay? Right. Okay, I will be solving with you another problem. In general, in the frames, I will be solving 4 problems with you to make sure that you understand the subject quite well, inshallah. So, example number 2. We are required to draw the normal force, the shear force, and bending moment diagram for the shown frame. Okay, this is hinged support. Here we are having an applied load of 2 tons, and this is 1.5 meters. And here we are having this distance is 2 and 5. This is a roller support. And we are having a distributed load here of 2 tons per meter, and we are having a concentrated load of 3 tons. This distance here is 2 meters and 3 meters. 2 and 2 meters. Now, we are going to get the support reactions. If this is point A, B, C, D, and E. Now, sigma Fx is equal to 0. We are having a force here of 3 tons. The only support reaction that will give us 3 tons is the support at A. It will be 3 tons. How can we determine the vertical reaction at A or the vertical reaction at E? We can take either moments about point E to determine the vertical reaction at A, or vice versa. So if we took moments here, we are going to get the resultant of the load 2 by 5 by 2.5, and don't forget the 2-ton force times its distance, which is 1.5, and the 3-ton force by its distance, which is 2, and the other reaction 3 by its distance, which is 4, and the vertical reaction at A multiplied by its distance, which is 5 meters. So if we did that, the value of AY will be equal to will be 1.6 tons. Sigma Fy is equal to 0. I'm going to get the value of EY, and it will be 8.4 tons. Okay? Now, after getting the reactions, we will start drawing the normal force, the shear force, and the bending moment as usual. Let me start first the normal force diagram. Let us decide on the side where we are going to draw the positive and negative moment. Again, the frame is shading the right hand side. So as if we are standing here. So we are standing here under the frame. It means that this is the near side and this is the far side. The near side is negative and here positive. The near side is negative and positive. And of course, for this central line, the near part is below and the far side is above. Type. Let us start part by part. For the column AB, if you take a section here, imagine that you are taking this portion only. You are having the 1.6 force vertical reaction. It should be equilibrated with normal force getting towards the section, so it will cause compression. يبقى I'm having compression force here equals to 1.6. What difference will it make if I'm cutting a section here or a section here or a section here? The same. I don't have any other forces applied along the side AB in the vertical direction. So this means that I'm having here compression and its value is equal to 1.6. Where should we draw the 1.6? We should draw it on the negative sides. يبقى the normal force is constant and its magnitude is 1.6. Very good. But let us take the part CD. If you take a section here like this, either that you take all of the frame or you are taking the upper portion, there is nothing except this force which is normal to the central line. It's not causing normal force. يبقى the normal force here is equal to 0. The same condition if you are taking a section here or a section there. يبقى therefore this part has 0 normal force. Type. For the part CD, don't take a section like this. Here you are basically taking two sections. You are cutting a section here and you are cutting a section here. You should avoid this because you are getting the unknowns. You don't want to increase the number of unknowns. So if you want to take one section only, you should take the section like that. شوف, we did not cut any other section. Now, what will be the normal force in this side? In order for this part to be in equilibrium, here, I am having 2 tons, and here is my cut section. I should have a 2-ton force like this, such that sigma fx is equal to 0. يبقى therefore the internal force that appeared is directed towards the section, يبقى it is compression. طبعا it is logic that if you did not think it this way, you are having this 2 ton, it is causing compression for this horizontal element. يبقى this horizontal element is subjected to compression. What difference will it make if you are cutting a section here, or you are cutting a section here, or you are cutting a section here? The same. When will it change if you are having any other force applied in the horizontal direction and we don't have? يبقى therefore I need to indicate -2 here. On which side am I going to draw that? I'm going to draw this below the datum because this is the side where we show the negative value for. So this is 2 and this is 2. Take care that the hatching is not decoration. It has a meaning. Now I don't want to see any one of you showing for me the hatching like this. You will lose marks in this case because the hatching has a meaning. What is the meaning of the hatching? For example, if I want to stand here and I want to determine the magnitude of the normal force, I will measure the diagram parallel to the hatching. يبقى the hatching is telling us in which direction we should measure. we should measure the diagram perpendicular to the central line. We should measure this diagram perpendicular to the central line. So this is the magnitude of the normal force applied here. Very good. Let us go to this portion. If you are cutting a section here like this to investigate the normal force, either that you will take the right hand side, and this is easier in my opinion, or you will take the left hand side. Imagine that you took the left hand side. Take care that we are not taking this portion only, or we are not taking this part. We have to take the all what we have. Okay? So you are having here 2, and you are having 3, and this is 5. This should be 5. Okay? Therefore, the resultant of the normal force is equal to 0, because the 2 and the 3 and the 5 will cancel out. Or if you want to think of it from the right hand side, there is nothing except this, and this reaction, it is normal to the central line, and the distributed force also normal to the central line. It will not cause normal force. Therefore, we are having here 0 normal force. This is the normal force diagram. It is telling us where do we have the normal. We are having the normal in the portion BC and in the portion AB. Okay? Now let's go for the shear. Let me erase this first. I will erase this. And I will draw the shear force diagram. Again, the positive shear is drawn above the datum, and the negative shear is drawn below the datum. Very good. Type. Let me start with the column AB. Where do we stand? We are standing here, right? Where is my left and where is my right? We are standing here under the frame. Therefore, this is my left hand side. Now I am having a force on my left hand side at point A and pointing upward. This is a positive shear. Therefore, I will come here and I will indicate positive shear. Okay. From this point to this point, I don't have any forces applied on the central line. This means that the shear should be constant. Therefore, the shear will be constant like this. And it is 5. Now I am having a sudden applied or a concentrated load applied. If you are going to account for this, this is on your left hand side and downward because we are starting from the left. This means that it will cause sudden reduction in the shear, so it will reduce to 2. This magnitude is 2. From this point to this point, I don't have any forces applied, therefore the shear will persist and its value will be positive 2. Always, whenever we are drawing the shear diagram, you have to indicate its value at either ends. This is 5 and this is 5. And here you are having 2 values because there is a sudden reduction in the shear. It reduced to 2. And here we are having 2 and here we are having 2. Then we finished the column AB. Type. How about the part CD? Again, we are standing here. Okay, we are standing under the frame. Now, I want to start from this point, but this point is on my right hand side, so it will reverse everything. You remember the positive shear. This is the positive shear, and this is the negative shear. Okay? The positive shear is on my left hand side and upward, or on my right hand side and downward. But the negative shear is vice versa. The positive shear is defined either it is on your left and upward, or on your right hand side and downwards. Now, if you want to work here from the right, because it is easier, then I have on my right hand side and downward a force of 2 tons. This is classified as a positive shear as well. If one of the students said that I don't want to work except from the left all the time, so this means that I will have to take a cut section here and consider all of the forces on my left. شوف بقى, all of the forces on my left. See? Now let us count the forces on our left hand side. I am having the 5 upward. I am taking all of this portion. I'm having 5 tons upward and 3 tons downward. The resultant is 2 upward, which means that it is a positive shear. So we reach the same conclusion, either working from the left or working from the right. So where should I draw the 2? I should draw the 2 at the far side, which is the positive. Here we are having, so this is 2 and this is 2. Type. Let us take the part CB. I'm now searching for the shear. I'm looking for the forces perpendicular to the central line. The force perpendicular to the central line I don't have. Now this force is causing normal force in the member BC and causing shear in the member CD. But when you are taking a section here and you are taking the left hand side, there is no forces applied perpendicular to the central line. This means that this part we don't have shear. In this part we are having 0 shear. Type. If you are cutting a section here like this, I want to determine the shear right of point B. I will take all of this portion. Okay? So I'm having the 1.6 upward and I don't have anything else. Because this is not causing shear, this is not causing shear, and this not causing shear. I'm looking for the force perpendicular to the central line. The only force that I have is the 1.6, which means that I'm having here an upward force of 1.6. When you are cutting a section here like this, you need to count all of the forces that you have. You are having 1.6 upward, and you are having 2 by 5, which is 10 downward. يبقى 10 negative and 1.6 positive. يبقى the result is 8.4 negative. Of course, it should be equal to the left to the reaction at point E. يبقى therefore here I will have, this is 8.4 negative. How do I connect between these 2 points? As long as the load is constant, يبقى the shear must be linear like that. This is positive shear and this is negative shear. What is the slope of this line? It is equal to the magnitude of the load. The slope of this line here is -2. Why is it negative? Because the load is pointing downwards. Okay? Let us go to the big guy, to the bending moment. The most important diagram that we have. We are depending on it on many things. So we are having here the bending moment diagram. This is the bending moment diagram. Again, the bending moment diagram, we are drawing the far side negative and the near side positive because we are drawing it on the tension side. So everything is reversed compared to the normal force and the shear. Okay, let me start with point A. If I want to determine the bending moment at point A, I will isolate this point here like this. Okay, I will take a cut section and take the lower part of the frame. I have nothing. The force is passing through the point and the vertical reaction is also passing through the point. This means that the bending moment here is equal to 0. طيب. The bending moment at this point, I will take the lower portion. Of course, the 1.6 is not causing bending moment, but the reaction 5 is causing bending moment. And how is it rotating? It is rotating in this direction. The tail of the arrow is on my right hand side. I'm going to draw the bending moment on the side of the tail of the arrow. Therefore this will be 10 meter ton. Okay? The bending moment here is 0 and the bending moment here is 10. I don't have any loads, the shear is constant. Therefore the moment must be linear. Okay, and this is positive. What will be the bending moment at point B? Take care. Always I want you to show me the free body diagram of this point, of point B and point C. Because there you are having so many members connected, you have to make sure that the bending moment is in equilibrium. Let me start with point B here to show you what we should do. For point B, we are having basically 3 points, right? This is point B. We can calculate the bending moment on the right and below, and the bending moment on the other side will be obtained from equilibrium. Type. From this side, you are having 3 multiplied by its distance, which is 2. It is rotating in this direction, causing moment 6 meter ton. And you are having 5 multiplied by its distance, which is 4. It causes bending moment in the other direction, 20. Therefore, the resultant will be in this direction here, 14. Again, how did I get the 14? 5 multiplied by 4, rotating in this direction. And 3 multiplied by 2, rotating in the other direction. So I am having 20 minus 6 gives 14. So the result here is 14. Very good. On the other side, left of point B, I have nothing except the 2 ton. The 2 ton force is rotating in this direction, right? Therefore, it is 2 multiplied by 1.5, it is 3. 3 meter ton. How can this point be in equilibrium? There should be another force in this direction like that. مش كده? And its value will be 17 meter ton. Now, when I draw the bending moment at the lower portion, it will be drawn 14 and it will be drawn on the right hand side, at the side where we have the tail of the arrow. And the bending moment on the left will be drawn 3 and it will be below the datum. And on the right, it will be 17 also below the datum. So let us draw this here. The 14 will be drawn here, like this. I'm sorry. This is 14 meter ton. Why did I draw the 14 here? Because we are having the bending moment like that. The tail of the arrow is on the right hand side. How do I connect the 14 with the 10? I don't have any forces applied here. The shear is constant. The moment must be linear. Okay? Therefore, this will be classified as a positive moment because it is drawn under the datum. طب سؤال. Now, what is the relation between the slope of this line and the slope of this line? They are not collinear. They are not having the same slope. Why? Because the magnitude of the shear is different. The shear here is 5, so this line is having a steeper slope. The magnitude of the shear here is 2, so this is having mild slope. That's why this line is broken. It's not in the same direction. Very good. The moment at point D, طبعا it is equal to 0, because if you cut a section here, there is nothing except the 2 ton force passing through point D, so I'm having the bending moment here is equal to 0. Type the bending moment at this part. Take care, point C, actually, let me draw point C here. This is point C. The 2 ton force is rotating in this direction. and it is causing 3 meter ton. How can this part be in equilibrium? There should be another moment like this, 3 meter ton. Therefore, where should I draw the bending moment on the part CD? It should be drawn on the left hand side. Here I am having, this is 3 meter ton. How do I connect the 0 and the 3? By a straight line like that. And this will be classified as negative because it is drawn above the datum. Type. The other horizontal part, the part BC, we are having the tail of the arrow is under the datum. طبعا this is the direction that will make point C in equilibrium. If this is rotating clockwise, this should be rotating anti-clockwise so that point C is in equilibrium. The tail of the arrow is under the datum. Therefore this part here will be 3. Type. At point B, we also calculated the moment to be 3, and the tail of the arrow is under the datum. This part is having a constant moment like this, and it is positive. One student will tell me, how come a negative moment is in equilibrium with a positive moment? No. This moment is in the direction of the in the clockwise direction, and this is the anti-clockwise direction, so they balance each other. This is just sign convention between us. We said that the moment when the tail of the arrow is above the datum, it is counted as negative, or it is designated as negative. It doesn't mean that it is negative, okay? But it is just its designation. And here, this moment is drawn below the datum, so it is designated as positive, but the actual direction of the moment that will balance each other. Here I'm having the direction of the moment is in the clockwise direction, and this one is in the anti-clockwise direction, then they are balancing each other. Also the same thing here. You don't look to the sign, but you look to the direction of the moment. Whenever you are getting these values, you have to balance the moment at point B. Then we are going to go to the classification, where should we draw the bending moment itself. Take care. If one of the students by mistake wrote for me this one to be negative, by mistake, I will still give him or her the full mark. Why? Because he or she drew the bending moment on the correct side. It is drawn below the datum at the side of the tail of the arrow. So I'm very much concerned about the direction where you are drawing the bending moment, because this will define the location of the steel reinforcement, as we said before. But let's proceed. On the right hand side of point B, we are having a moment of 17 meter ton. Where is the tail of the arrow? It is below the datum. Therefore I will come here. Let me draw this with another color so that it is clear. I am having here 17. Very good. This is drawn perpendicular to the datum, which is CBE. Now point E, we are having 0 moment. This is a member where you have got the moment in the beginning and the moment in the end. If I don't have any forces, then I'm going to just connect them together. But now I'm having a distributed load. So I'm back to the principle of superposition. I'm going to connect this with a straight line. This is the shape of the bending moment if I'm just having end moments. But I don't have this case. I'm having end moments in addition to the distributed load. So I'll have to superimpose the bending moment due to the distributed load. It will be something like that. Okay? I'm connecting. This is here 14 meter ton. I am connecting these 2 points by a straight line, and then from the middle I am suspending a parabola. The magnitude of the parabola is equal to how much? The load is 2 and the span is 5. So it is 2 multiplied by 5 square over 8. Okay? So this is 50 over 8, which is 6.75, I believe. Okay? And you should hedge the distance between the original datum and the final curve that you have reached. Take care. We all know that the magnitude of the shear is equal to the slope of the tangent to the bending moment diagram. This point is the point of zero shear. It is corresponding to the point of maximum bending moment. The maximum bending moment is not necessary to be exactly in the middle. It can be shifted a little bit towards the side. Of course, it is shifted because this is 1.6 and this is 8.4. This length cannot be equal to that length. So it is a little bit shifted towards the left. Okay? So this will be the shape of the bending moment. Don't worry about the intersection of the bending moment. This is the bending moment for the column. This is for the beam on the left, and this is for the beam on the right. Based on this bending moment, we can predict the steel reinforcement. This is just for our knowledge. You're not going to be examined in this point, but you just understand why we are doing all of this. If I want to see how will these guys reinforce the frame, then the frame, if it is in the real life, it looks like this. Because we drew the bending moment, unlike 212, we drew the bending moment here on the tension side, and we know that the concrete is weak in tension, so it needs help, needs steel reinforcement. The bending moment is drawn on the left. It means that we are having cracks here. The bending moment is drawn below the datum. It means that we are having cracks here. The bending moment is drawn to the right of the column. It means that we are having cracks here. And the bending moment is drawn under the datum. Therefore, it means that we are having cracks here. Because here we are having the tension, and here where we are having the compression. How can this be safe and it will not collapse? I will put the steel reinforcement like this, so like that. The steel reinforcement will be on the tension side. It will take the tension because the concrete cannot support the tension. And the main reinforcement in the column will be on the right hand side because we are having the bending moment like that. So it will be like this. Okay? Now we should start thinking of assignment number 5. The solution of, or the analysis of frames. You will be required to determine the support reactions, the normal force, the shear force, and bending moment diagram. But yet I am going to solve with you another 2 problems in the coming lecture. Okay, thank you.